Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video lesson is for introductory transport phenomena based on the Welty, Rohrer, and Foster textbook. We are looking at Chapter 2, Fluid Statics, and specifically on Section 2.3, Forces on Submerged Surfaces. So let's consider a vertical rectangular wall. The force at any point on that wall is going to vary due to the weight of the fluid pushing against it. Let's look at the resultant force on that wall if we neglect or ignore for the moment the atmospheric pressure. We would typically define pressure as force per unit area, but we can think of that alternatively as the force is the integral of the pressure over the area. And in this case, we know that because this is a fluid, from 0 to h for the height, rho g z times the area of the wall is going to give me my overall pressure at any particular location. Now in this case, I only have a single fluid, so the rho is going to be constant. G, gravitational force, is constant. So I can pull each of those out. And area, the height is varying as I go from height 0 to z. Or z goes from 0 to h, I guess. But the width, b, is going to be the same. So therefore, in this particular case, Fr is going to be rho g, those are constant, 0 to h, z, and then b dz. Okay, but b is also constant, so I can pull it out also, rho b g, 0 to h of z dz. Integrate that. Rho g b 1/2 z squared from 0 to h, and so rho g b h squared all over 2. Okay, well, what do we do with that? Well, what is the area of this face? B times h. So B and one of the h's is going to be my area, so Fr is going to be 1/2 rho g, the other h, and then the area of the wall. What this tells me is that the resultant force is 1/2 the pressure at the base of the wall okay, that's the rho GH, times the area of the wall. So this leads us to the concept this is commonly called the pressure prism. And it's used as a very quick way of doing calculations of the resultant force on a vertical wall. And you can even apply this to a mini layered system where you had different fluids floating on top of each other. And you can use this prism effect. So let's look at an example with two fluids. And in this case, we're going to have a vertical surface that has two fluids. Top layer is 1 meter deep. Specific gravity is 0.98. And the next layer is 3 meters deep with a specific gravity of 1.04. Now, if we do this, let me just sketch this for you very quickly. So, okay, in my drawing, what you can see is the two different liquids, and then there's this wall over here. And this is a solid wall, like built into the dirt, something like that. So the wall is not subjected to atmospheric pressure. So we want to find the absolute pressure on this wall. So we're going to need to include the atmospheric pressure. A lot of times we'll do it by indicating where the atmosphere is being applied with a little upside down triangle. And in this case, P atmospheric we will take to be 101 kilopascals, or if you would rather, 101,000 newtons per square meter. Okay? Now, I'm going to work this problem using the pressure prism approach. In the book, they do a very similar example, doing integration and pressure as a function of height. Okay? You're going to get the same answer either way you do it. I wanted to give you an alternative so that you can see the things that you might hear from other places. If you're taking a mechanical engineering course, this is more typical of what one would do. In our textbook, they're trying to build up some math formalism that we will be needing later, and so they're going to take kind of a more theoretical approach often. Nothing wrong with that, but I want to give you both points of view. If you look at this, then what we have, and that should be 3 meters, is that we have a pressure at the top that is atmospheric pressure at point 1. At point 2, the bottom of the top layer, that's 1 meter below that, we're going to have another pressure that's due to the weight of that top fluid. And then at the very bottom, we're going to have the pressure that is due to the fluid at the lower level, right? Okay, so we can evaluate each one of those. So P at the top, we know is atmospheric. So it's 101,000 newtons per square meter. P2, we know, is the atmospheric pressure plus the rho of that top layer times G times that height of 1 meter, okay, which is 101,000 newtons per square meter plus 980 kilograms per cubic meter. G is 9.8 meters per second squared, and the height is 1 meter. Okay, this is going to give me kilograms per meter per second squared. I need G sub C. You always are going to need G sub C. So in this case, it's 1 Newton second squared is 1 kilogram times a meter. And if you do this, this tells me that P2 is equal to 110,604 newtons per square meters, or pascals. P3, similarly, is going to be P2, what's at the top there, plus the density for layer B times G times 3 meters, which in this case is our answer we just got, plus 1,040 kilograms per cubic meter times 9.8 meters per second squared times 3 meters. Our G sub C and thus P3 is equal to 141,180 newtons per square meter. Okay, that tells me all of the pressures. What about the force? Well, the force is now that pressure prism. So the force at the top is 1/2 the average of those, those two pressures, 110,604 plus 101,000, the top and the bottom, okay, times the area. It's 2 meters wide, 1 meter tall. And for the second layer, it's 1/2 110,604 plus 141,180. And this one is 2 meters wide and 3 meters tall. Okay. The units here were newtons per square meter times square meters, so this is all going to be in newtons. The force, therefore, is 211,604 newtons plus 755, 352 newtons, or 966.956 kilonewtons. Okay, probably that's ridiculous sig figs, and I would go with 967 kilonewtons. So, what if the back side of the wall was also exposed to atmospheric pressure? In that case, you would neglect the atmospheric pressure. So P1 for our previous drawing would be 0. P2 would be density at the top times G times the 1 meter, 9604 newtons per square meter. And P3 is 9604 plus PB G times 3 meters is 40,180 newtons per square meter. The force in this case is 1/2 9604 times 2 times 1 plus 1/2 9604 plus 4180 times 2 times 3. The force is 9604 newtons plus 149, 352 newtons, or 159 kilonewtons. Okay. Now, if you want to do it the way it's done in the book, they're going to take an equation, put it in terms of P as a function of Z, and integrate that. So the integral of P times B dz. Now we can also make things more general by allowing for a slanted wall. So in this case, if I have a wall that's slanted at an angle theta, so the height measuring straight vertically is h, and the direction y is the length of the slanted wall. Okay. In this case, h is y times sine of theta. And so the pressure is P naught plus rho GH, but that's y sine theta. And so the resulting force is, integrate this, P naught plus rho G y sine theta all over area dA. It's P naught A plus rho G sine theta integral of y dA. Now this last little bit here, this is the first moment, or also called the centroid of the surface. Okay. And we tend to think about the centroid as being the location where a force at a point would like exactly balance the object, right? If you wanted to spin a plate on your finger, you would need to know where the centroid is. Okay. That's going to be true when the pressure is constant, like say in air, but with a liquid, the pressure is going to be always greater below the centroid and less above it. So as a result, the center of pressure is always going to be below the physical center or centroid. Let me write that down. So once again, the center of pressure is always below the physical center or the centroid. So if you had something and you're holding it horizontally, the centroid would be the entire game. But now then where you need to balance it for the pressure is going to be a little lower than that because of that additional weight of the fluid. This concludes this lesson from Chapter 2, and next we will be looking at buoyancy. Thank you very much for your time.